All right, so at the very beginning of this lesson on series, I referenced something called Zeno's paradox in that Frank and Ernest cartoon. So example 2 also references Zeno's paradox, which can be represented by this infinite series. We have the summation from n equals 1 to infinity of 1 over 2 to the n, which is equal to a half plus a fourth plus an eighth plus a 16 and so on, right? Infinitely long. It's supposed to add up all of those terms. Okay, now here's the thing. This is another way to think of one of Zeno's paradox. I am starting at 0 and I'm trying to go up to this number 1, right? But before I get there, I need to go halfway there. Okay, after I've reached the halfway point, now I need to go halfway from my halfway point to my finish. That's adding an extra quarter. Okay, and now I need to get halfway again. That's adding an eighth. Now I need to go halfway again. That's adding a 16th, right? So what we want to know really is that are we actually going to reach the number 1? Zeno says no, you would never actually reach your destination if you keep taking half of the distance that you have left over. And we're going to see if we can resolve this using calculus and using a sum of this series. We're going to see if it sums to the number 1, because if it sums to the number 1, we do get there. We actually do get there. And how do I find the sum of an infinite series? I start with partial fractions. Partial fractions? I mean partial sums. Yeah. All right, over here we've got an XKCD webcomic that also references Zeno's paradox, if you wanted to enjoy that. Okay. All right, so I'm going to start with some partial sums. The first partial sum would just be the first sum, which is the first term, which was a half. I went halfway there. Okay. The second partial sum would be the first and the second terms. It's a half plus a fourth. Half and a fourth, that gives me 3/4. I'm 3/4 of the way there. Okay. The third partial sum is going to take a half, a fourth, and an eighth. So that'll be the 3/4 that we got before. We're going to add an eighth to that. 3/4 is 6/8 plus one more. We have 7/8. We're 7/8 of the way there. All right. And then keep going here. I'm going to add in the extra 1/6 for the next stage, 1/16. And let's see, that would be 15/16. 15/16. Okay, and then here's the nth partial sum. I just go all the way up to 1 over 2 over n. Okay, so we have these partial sums, and we want to now form a new sequence with these partial sum values. So I'm going to make myself a sequence that looks like this. 1/2, 3/4, 7/8, 15/16, and so on. And now I want to see what's it look like that thing's approaching. Well, in exercise 1, example 1, we had an equation that we could take the limit of, and that's what we want here. We just don't have an equation, we have to come up with it. Okay, so here's the challenging part. Like, how do I get an equation that's going to determine each one of these little fractions? Well, I'm going to take it in parts. I think the easiest thing to do is look at the bottoms. We got 2, 4, 8, 16. What do those look like? Don't those look like just powers of 2? You got 2 to the first, 2 to the second, 2 to the third, and so on. So the bottom is just 2 to the n. It's sort of like exactly what we started that the entire series with, right? It was 1 over 2 to the n. Okay. And now the tops. I got 1, 3, 7, 15. Well, they're odd numbers, first of all. Oh, but look, aren't they just 1 less than the number that's underneath it? So I got to 2 minus 1 gives me 1. 4 minus 1 gives me my 3. 8 minus 1 gives me my 7, and so on. So these are just 1 less than a power of 2. 1 less than a power of 2, then that's going to look like 2 to the n like we get before, and then just subtract 1 from it. Okay, so if I put those two things together in a ratio, I have an equation that gives me the nth partial sum. So if I wanted, say, the 5th partial sum, just plug 5 in for n, work that thing out, it'll give you the sum of the first 5 numbers. So what we want to do is find the limit of this as n approaches infinity. What is this sum getting closer and closer to? All right, now, whenever I take a limit of something, the first thing to do, of course, is just to substitute in this case, your n value. If you plug in infinity, you'd have infinity over infinity. Sounds like L'Hopital's rule. So we take the derivative of the top, the derivative of the bottom. Derivative of an exponential is still just an exponential. It's 2 to the n, but then you have to multiply it times the log of the base, so times natural log of 2. And notice that's identical, the top and the bottom. They're exactly the same, which means they cancel out, and it gives you 1. What's that mean? It means that this sum is getting closer and closer to the number 1. It converges to 1, and that's the sum of the series, right? If we add up an infinite number of these numbers, it's getting closer and closer to 1, and this resolves Zeno's paradox. So Zeno is saying, no, we never get to the number 1, but we were able to show that you can get to the number 1. It's just going to take a while. All right, I got a couple more pictures for you. This next one is just a table of values that's showing you the progression of summing up these numbers all the way up to number 25. And you can see that even on the 25th sum, yeah, you're pretty close to 1, right? Okay, and then a little graph, Zeno's paradox of teaching, comparing number of times I've taught something and how well I'm teaching it. And then finally, here is a geometric interpretation of this exact same thing. So instead of looking at it on a number line, this looks at it from the area of a square being 1. It's a 1 by 1 square. Okay, so first I fill half of it, and that's the blue part that's right there. And then I take half of the half, that's the 1/4. Take half of the 1/4, I get an 1/8. And you can see as I keep progressing in this diagram that I'm filling it up. I'm getting closer and closer to that area of 1. This is a geometric interpretation for something that is called a geometric series. So this Zeno paradox example is an example of a geometric series. And so in the next lesson, we'll talk about the details of this geometric series. It's very popular. It's very important. It's always on the AP exam. And then what are the different parts of this thing? And then what does it actually sum up to?